Hi everyone, I'm Marina. As a YTsaurus team member, I am in charge of developing Query Tracker. Today's webinar is about various SQL engines that are supported in YTsaurus. First, I'll tell you what Query Tracker is, how to use it, which SQ50 engines it supports, and what it has under the hood. I'll also supply some info on how to maintain and administer it. Then, I will tell you what you can use Query Tracker for and how it generally works. Finally, we'll move to the cluster. You aware I will show you some specific steps to use Query Tracker. Let's see the YTsaurus flowchart. We store data in static and dynamic tables. You can query such tables directly by running simple reading queries through the APIs. However, this is not always the best option. Sometimes, you may want to calculate some complicated analytics without downloading a huge table to your local computer. This is when query languages, such as SQL, come into play. Traditionally, we have 4 engines to process SQL queries. The first one is YTsaurus, that converts SQL queries into MapReduce operation graphs. Then, there are CHIT and SPIT languages. You can learn more about them in the relevant videos on our channel. Finally, we've got YTquery language. We created this dialect to specifically get access to dynamic tables. This is why we created Query Tracker to orchestrate all those languages and queries based on them. With Query Tracker, you get the common logic for using all 4 SQL dialects I mentioned before. Let's see how you can deploy Query Tracker within a cluster. You can run a query both from the UI and through a programming language SDK and a command line. Your query then runs through the cluster proxy, where the primary authentication occurs. After that, it gets to Query Tracker unchanged, and then it gets routed to the relevant subsystem. This is all deployed through the Kubernetes operator. All you need to do is specify all required components in the cluster specification. Query Tracker is a stateful component. This means it has a state that is stored in the dynamic tables. There are 3 main tables. First, there is a table for active queries that houses info on all queries that are currently running. Then, there are 2 more, one for the finished queries, which also has metadata, and one for the results. The metadata table for finished queries also has 3 index tables. You only need those to quickly retrieve data from it. Any user query in Query Tracker is a common API call. Start query allows you to start a new query. Abort query allows you to abort an existing query. With get query result, you can get the query result metadata. With requery result, you get the query result. Get query allows you to retrieve metadata on both a finished query and a query in progress. With list queries, you can get the list of the existing queries, including those filtered by start time, end time, user that started the query, and so on. For instance, you can get the latest 20 queries started by a certain user. Finally, alter query allows you to modify the query metadata. Let's see how a single query runs through its lifecycle. To start a query, a user makes an API call through start query. As any other request to YTsaurus, this query runs through the proxy and gets to Query Tracker unchanged. Query Tracker does 2 jobs at the same time. First, it processes the API calls it gets. For start query, this query was written to the active query table to further get executed. Second, Query Tracker launches tracking active queries. Once in a while, all active query trackers scan the active query table for the new ones and take them for processing. The tracker in charge of a certain query sends it to the relevant subsystem, tracks its progress, fills in all required metadata, and monitors its status. Once the query is complete, it's moved from the active table to the finished query table. Further on, when a user wants to get info on the query status or result, this info is retrieved from one of the system tables. This concludes my intro on how it generally works. Now let's start our query tracker demo in the cluster UI. So, this is the cluster home page. To navigate to the query tracker page, select Queries in the side menu. I've got this tab in Recently Opened. If you are opening it for the first time, it may be in the main list instead. Once you open this tab, you land on a page where you can create a new query. Let's do it. We can see it gets processed and returns the result quite quickly. You can download the result in any format you need by providing some additional properties. Let's download it to get a file with a dataset. Quite easy and useful, isn't it? In addition, the query appears in the history of all queries, both created by me and those available to me. In the query history, you can change the query name. This may be useful for both arranging the query list in a more convenient way and appropriate filtering, with which you won't lose the important queries. Apart from the result, there is some other metadata available to you, such as the query ID, start time, end time, user that started the query, and the access control object list. Access control object, or ACO, is a tool that manages access permissions for a query. Each query gets a list of multiple ACOs, each providing certain permissions to a certain user. In our case, the list only has one item, nobody. This is a system ACO that does not provide any permissions to anyone. If you want to change this, you will need to expand the list. For demo purposes, let's go to the command line, create a new ACO, and see how it works. To do this, we need to run a few commands. First, we need to create an access control object in the query's namespace with any allowed name. Let's call it Analytics, assuming we're creating it for the analytics team. Then, we'll need to use the principal_ACL property, where we will specify which permissions it will grant and to whom. In our case, it will provide permissions to analysts that have a relevant dedicated group on my cluster. You can also specify some specific usernames here. Now, let's see which permissions to grant. All permissions fall into three groups: use, read, and administer. Use allows reading the text of a query. With read, you can read the query results, while administer allows you to modify queries, such as assign or revoke access permissions, change metadata, and pause queries. In my case, I assume I only need the analysts to read queries. They won't need to modify them. That's why the read and use permissions are sufficient. Let's go back to the cluster UI. We'll need to refresh the page so that it applies our recent changes. Now, we can edit the ACO to add the analysts there. Once we are done, any user from the analyst group will get access to this query. They can access it both using the direct URL that has the cluster address, queries, and the query ID, and through the history of the available queries. Here, I've got my queries as well as the administrator query, which I can access right because the relevant ACO says so. If we take a closer look at it, we'll see the list only has a single item, everyone. This is also a system object that allows all cluster users to read the query text and result without modifying it. This means if I want to change the query name, I won't be able to do it. Likewise, if I want to open the query I don't have access to, I will get the relevant error saying I cannot even read the text of this query. All right. Apart from ACOs, there is another option to grant access to a query, which is the Share button. Once I click this button, any user having the direct URL to the query will be able to read both its text and the result, again, without any permission to modify it. This method is much easier to use. You do everything with a single click. Well, with 2 clicks to be more precise, as you've got both share and unshare. However, this is far less secure than the echo. When it comes to the echo, you can fully manage who gets the permissions and what permissions. In case sharing the queries directly, any random user with the link will be able to read queries they probably should not read. To specify the echo permissions with which the query will run, you just need to tick the relevant checkboxes with the appropriate permissions. This concludes the part dedicated to security. Let's now move to other features. Let's start with the tutorials. A tutorial means an option to upload some well-documented queries to the cluster for the purpose of training new users. In our case, a cluster admin uploaded some YTsaurus and YTchit queries that can be a good addition to the documentation. They are well commented and allow you to better understand the cluster purpose. VCs, or version control system, is another feature of Query Tracker. You may want to use it to save certain queries that you run frequently or regularly and then reuse them as needed. This feature is native to Query Tracker. In order to make it work, the cluster admin should specify the systems to use in the settings, and then provide tokens for those systems. In this case, I specified my personal GitHub token. After that, any cluster user may use this system with this token and get access to the relevant repositories. You just click one button to fetch the query and another to run it. Quite easy and useful, isn't it? Next feature I'm going to tell you about is navigation. When writing new queries, you will typically need to remember specific table paths, precise column names, types, and so on. Quite a lot of information that is difficult to remember and always needs checking. To avoid switching to another tab to view the table path or schema, Query Tracker offers a native navigation feature. You can use it to find the relevant table, see which columns it has, and, even more, create a query template. The system is asking whether I want to overwrite the previous one. I don't need it. It just has a simple select query, nothing special. So, we get a complete list of all columns the table already has. It is quite easier to tweak the query as you may need based on what we already have here. This concludes the general part on Query Tracker. Now I'll briefly outline the cases when you may want to use each SQL engine we have. Let's start with YTchit. This is a traditional ClickHouse dialect our YTchit subsystem runs. I already have a query for it. In general, you may want to use this engine when you have short queries you want to run right now. It is also useful for charts and dashboards. For demo purposes, I'm generating some data. For each day, I am generating 100 points based on normal distribution. Then, I am calculating a median for each day. You can also use a table residing on the cluster as your data and calculate any analytics you need. Once I got the data, I can start building a chart based on it right in the Query Tracker UI. I'm selecting days for 10 and values for Y. This way, it becomes much easier to analyze the data. The next engine we'll briefly talk about is YTquery language. This dialect was specifically created and optimized with dynamic tables in mind. It is not fit for working with other types of tables. If you need to create a short query to a dynamic table, YTquery language is just what you need to demonstrate its abilities. Let me remind you that the state of query tracker is also stored in dynamic tables, and you can analyze it too. For instance, you can view all queries that I created and ran today. Autosuggest is helping us with the paths. Let's now filter the queries by user, that is myself. And here is the query history we need. Right. Apart from just analyzing your queries and viewing the history, you can also leverage this feature to see who uses Query Tracker on your cluster, how much it is used, which engines are most popular, and so on. You can also view how large the results are. The only thing to consider is that you need to have access to the relevant table. Usually, the cluster admin should have it. The next engine to talk about is Spit. This is basically Spark SQL run by our Spit subsystem. This one is designed for large amount of data and large and complex queries that use a lot of join operations. Even the demo example takes some time to complete, which is why I ran it in advance. We basically had two tables, 3 GB each, and joined them. The query ran for 30 seconds. There is an important thing to consider when running Spit queries. In the query settings, make sure to specify the discovery path of the relevant Spit cluster. In this case, it is home/Spark. The last engine we'll talk about is YTquery. This is a graph engine that converts SQL queries into MapReduce operation graphs. It is also designed to work with large amount of data. In this case, I am just running a select with grouping from a 3 TB table. It will be completed in 4 minutes. You can track the query progress as it is running. You will see the changes here. Once it's complete, it will still be available. You can view which stages it ran through. You can also see what happened within each single operation and how much time it took to complete each one. Here, we can see that the map operation was the longest to complete. There are some stats too. In particular, they show the data size and the time to complete. Graphs, timelines, and stats may also be handy when optimizing your query. For example, if you have some queries that take hours to complete, you can use this visualized data to simplify them so that they run faster. Working with large data is not the only advantage of YTquery. This engine has been developed and maintained for years, and it has a lot of constructions to use for various types of tasks. For instance, let's take a case when you have a directory where you put the logs or product changes every day. Let's assume we want to analyze all those tables in a single run. This could be a challenging task for many engines, but not for YTquery. Well, for this task, you've got a specific construction. You can specify the range in the directories where you have folders. That is, the start table and the end table. Everything else will just run in the background. You won't need any additional join operations or analytics. In our example here, we used tables that are not that large, each around 1,000 rows. This is why the query did not take a lot of time to complete. If you look at the plan, you will see there were no MapReduce operations. All stages are DQ stages. DQ means optimization for small queries. That is, if your data is not that large, all calculations occur within the memory, the system does not waste time on launching operations and data materialization, which significantly reduces the time to run small queries. If you take a closer look, you will see I am using native functions for mean and standard deviation. Query language has a lot of other native functions, too. If this is not enough, you can create your own with Python. Python is well supported in it, too. Here is an example of a query we prepared in advance. It took 3 minutes to complete. Here I am using a Docker image with the environment I need. It also has the Python version I need, 3.11, as well as the libraries required for this example to run. Then, I am writing a script that launches a model that will answer my questions. I asked it why the sky is blue. I launched the model asking why is the sky blue, and got the result. In fact, the response is quite comprehensive. Apart from using a specific string as a prompt, you can also launch this script on top of a table and get the response in a certain column. Alternatively, you can avoid using machine learning models and just create your own function in line with your business needs. This concludes this YTsaurus overview and, generally, this Query Tracker webinar. Thanks everyone for watching. If you have any questions, feel free to ask them in our community chat. You can also read our help docs to learn more about what we slightly covered today. See the links in the description of this video.